this lecture is part of an online course of multivariable calculus, and I'm gonna solve some examples about linear approximation. So let me start by example 1. Find equation of the tangent plane. Find an equation of the tangent plane of z equals to square root of xy at the point 1, 1, 1. Okay, so I know that the tangent plane has the normal vector as partial derivative with respect to x at the given point, the partial derivative with respect to y, and also -1. Okay, so I need to find the partial derivatives first. So I'm gonna write this as xy to the power of 1/2. So fx would be 1/2 xy to the power of -1/2, and derivative of the inside function, which is xy with respect to x, is just y. Okay, and so I'm gonna plug in 1, 1, and so I get 1/2. I'm gonna do the same thing for finding partial derivative with respect to y, and if y at the point 1, 1 is again 1/2. So the normal vector would be 1/2, 1/2, and then -1. So equation of a plane that passes through the point 1, 1, 1 with this normal vector, it would be 1/2 x minus 1 plus 1/2 y minus 1, and then minus z minus 1 equals to 0. Okay, very good. If I'm looking for the linear approximation in here, you know that you just need to keep z in one side and write everything else on the other side. Okay, and in that case we have equation for the linear approximation. So z equals to 1/2 x minus 1 plus 1/2 y minus 1, and then negative times negative positive plus 1. That's the linear approximation of this function case. Okay, that was example 1. Let's look at example 2. Find the linear approximation of f of x and y equals to x over x plus y at the point 2 and 1. Okay, so for that I need to find partial derivative with respect to x. So I have the quotient rule to use. So x plus y squared, derivative of top with respect to x is 1 times bottom, so x plus y, minus derivative of the denominator with respect to x is 1 times x. Okay, so this is y over x plus y squared, and I'm gonna plug in the given point 2, 1 into that, so I get 1 over 3 squared, which is 1 over 9. I'm gonna find f with respect to y, so the quotient rule, denominator square, derivative of top with respect to y is 0 times bottom, 0, minus derivative of the bottom with respect to y is just 1 times top. Okay, so I get negative x over x plus y square. I just basically rewrote that. If y at 2 and 1, it's negative 2 over 9. Very good. So the linear approximation would be approximately the linear approximation would be what? The partial, let me write the formula first. So just as a recall, x naught, y naught, x minus x naught, plus the partial derivative with respect to y at the given point, y minus y naught plus z naught, which would be f of x naught and y naught. Okay, so that was a recall. So the linear approximation here would be the partial derivative with respect to x minus x naught is 2, plus partial derivative with respect to y is negative 2 over 9, x minus, I'm sorry, y minus, y minus y naught is 1, plus the value of the function at that point. I'm gonna plug in 2 over 2 plus 1, so I get 2 over 3. Okay, that's the linear approximation of this function. Let's look at the third example, example 3. Find a good approximation of, actually find a good linear approximation, I should say, of the function 1 plus x ln of xy minus 5 at the point 2 and 3, and then approximate f of 2.01 and then 3.005. Okay. For finding the linear approximation, I need to take derivative of that with respect to x first. So with respect to x, I get what? I have a paradox rule to use because I have a function of x in here. I have another function of x in here. Would be derivative of the first one, which is 1 times the second one. So ln of xy minus 5 plus derivative of this one times that. So I'm going to write x and I'm going to take derivative of ln. So let me give you a recall. Ln of any function like u, derivative of that would be u prime over u. Okay, so now I have a fraction, denominator would be the inside function, and then derivative of top with respect to x would be just y. Okay, now I'm gonna plug in the point 2 and 3 into the partial derivative. I get ln of 6 minus 5 plus 2 times 3, 6 over 6 minus 5, which is just 1. So this is 1. ln of 1 is 0, so I get 6 as fx. Now let's calculate fy. I get a 1, which is 0, plus, in that case that I'm taking derivative with respect to y, x would be a constant, so I'm just going to write x, and then derivative of natural log, one more time, would be derivative of inside over xy minus 5. So derivative of inside with respect to y is just x. So it would be x squared over xy minus 5. Plug in the point 2, 3 into here, I get 4 over 6 minus 5, so the answer would be just 4. Okay, now the function f is differentiable. As you see, f is differentiable. Why? Just because we saw in the other video that if partial derivatives, they exist and continuous, both of them, okay, at the neighborhood of the point 2 and 3, then f is differentiable. Okay, let's look at that. Fx has this formula. Okay, so fx exists at the point 2 and 3. I got a number, so it exists. it's defined. It's defined. And is it continuous? Yes, if xy inside natural log, I should have greater than 0. So it's continuous at xy greater than 5. Okay, and I don't want to make it equal to 5. It's just because it makes my denominator 0, which is not good. So fx is defined because I got a number, and it's continuous. ln is continuous when the inside function is positive, and I have a fraction of polynomial on top, polynomial on the bottom, and the denominator is not 0 on this interval, which the neighborhood of 2, 3, any neighborhood that is close to that would satisfy this condition in here. How about here? For partial derivative with respect to y, let me bring this one a little down. Okay, and you see that it exists, it's defined because I got a number at the end. And if xy is not equal to 5, it's continuous, which is the case on the neighborhood of 2 and 3. So that's why the function f is differentiable at the point 2 and 3, and therefore the linear approximation is good. Is a good approximation. It's very close to the value of the function. Okay, now let's write the formula for the linear approximation. So L of x and y is equal to the partial derivative with respect to x at the given point, x minus 2, plus partial derivative with respect to y minus the given point, plus the value of the function at the given point. What is f of 2 and 3? Let me plug it into here. F of 2 and 3 is 1 plus 2 ln of 6 minus 5, which is just 1. So this is 0. So f of 2 and 3 is just 1. Let me say that it's 1. Okay, so f of, what was the point? Okay, 2.01 and then 3.005 is approximately L of this 1 and then 3.005. Okay, so all I need to do is to plug in this point into here. I get 6, then 2.01 minus 2 plus 4, 3.005 minus 4 plus 1. Now just calculate that. This is 0.01, and this part in here is actually negative, oh, actually not 4, it's 3. I made a mistake in here. This is 3, so that's why this is just 0.005. And so I get what? I get 0.06 plus this is 0.02 plus 1, which is 1.08. So this is approximately 1.08. Very good. That was example 3. Let's look at one more example. Example 4. Verify the linear approximation. This 2x plus 3 over 4y plus 1 is approximately 3 plus 2x minus 12y at a given point 0, 0. Okay, so my function is given, f of x and y. I need to find partial of that with respect to x I need to use quotient rule for y plus 1 squared derivative of top times bottom minus derivative of the denominator with respect to x, which is 0 times top, 0. Now I'm gonna plug in the given point 0, 0 into that, so I get a 0, I get 2 over 1 squared, so the answer would be 2. How about if y, again quotient rule, derivative of top with respect to y is 0 times bottom, 0, minus derivative of the denominator with respect to y is 4 times that, so 4 times 2x plus 3, so this is negative 8x minus 12 over 4y plus 1 squared. So if y at 0, 0, plug in 0, I get negative 12 over plug in 0, I get 1, so this is negative 12. So the linear approximation would be partial with respect to x, x minus 0, plus partial with respect to y, which is negative 12, y minus 0, and then the value of the function at 0, 0. Plug in 0, 0 into here, I get 3 over 1 plus 3 over 1. Okay, as you see, this is the linear approximation. Let me simplify that. 2x minus 12y plus 3, which is this part, the linear approximation. Okay, so we verify that this is the linear approximation.